So, we just continue our previous discussion on an oscillator with damping and forcing. Now, I will formally introduce the case where you have both damping and forcing are present. So, why this is interesting? Because this is actually the most natural case we can see in everyday life. For example, I just gave you a very common example of the swing in a park. So, now you see, like when you go to a park and your friend is pushing you and you are sitting in a swing and your friend is pushing you periodically, then basically you have to understand that you are moving in air. So, that air also has some drag or dissipation force or viscous effect, so that it always try to oppose the motion. Okay. And if you take all these things into account, then finally, as you can understand that you will have a resultant equation for dynamics, which should be looking like this: x double dot plus 2 lambda x dot plus omega 0 square x is equal to f by m cos gamma t plus beta. Once again, I am just taking the real equation as for now. Okay. So, this is the acceleration, this is the damping part, and everything I actually have divided by m, and this is the restoring part, okay, which is also seen in the case of natural oscillation, okay, without any forcing and dissipation, and then this is the force part. So, this equation is a second order ordinary differential equation which is linear, but this is non homogeneous because of this term. So, as you will see that here I have the second order term as well, I mean the second order term, okay, second order derivative of x with respect to t. I also have the first order derivative of x with respect to t, okay, and I have some trigonometric term which is a function of t. Okay. Now, what to do with all these things? So, first point is, since this is non homogeneous, we have to consider the solution. So, x t will be again the superposition of a complementary function and a particular integral, okay, that we have to understand. And then we will see that this case is a little bit complicated with respect to the previous cases, okay, which were somehow simplistic, and that is why right from the beginning we can, from our side, we can make one degree of simplification. We can forget this initial phase of beta, we can set this beta to be equal to 0. Okay. Now, if you do that, then you will simply have the equation to be x double dot plus 2 lambda x dot plus omega 0 square x is equal to f by m cos gamma t. Okay. Now, how to solve this? So, since again the point is that complementary function, particular integral, and we even do not know whether we have to include the case of resonance and everything. So, the best way is to cast the best way. So, I am again trying to make this clear that you are not always bound to do, I mean, cast the equation in a complex form, but it is often very advantageous. Okay. You will have the global view of the solution, okay, in this way. So, the best way to cast the equation in complex form. Okay. So, which I can write as z double dot plus 2 lambda z dot plus omega 0 square z is equal to f by m simply e to the power I gamma t. There is no phase. So, that means even with this I have a real amplitude, okay. That is something we can make. We search for a trial solution, okay. So, the trial solution we search, okay, and we can again say, okay, that we again trust on our everyday experience, where every such forced motion finally follows the force's periodic nature, the periodic nature of the force. Okay. Then we say, okay, we just try with this solution and we see what happens. Z is equal to B times e to the power I gamma t, and this B is not necessarily real. So, that means we can say, although I can make the force to be with 0 initial phase, the displacement can have some initial phase, and that possibility I want to keep alive over here by keeping this B to be a complex amplitude. Okay. If you do this, so then your Z dot will simply be, but this is constant of course, I gamma B e to the I gamma t, and Z double dot will be minus gamma square B e to the power I gamma t. Okay. And simply, so putting those in the main equation, you get, or we get, whatever. So, B common minus gamma square, okay, plus 2 lambda I gamma plus omega 0 square is equal to f by m. Remember, I have assumed here, which is completely understandable, e to the power I gamma t is not equal to 0, and that is why I take this out from both sides. Okay. And then what will be your B? Your B will simply be f by m times omega 0 square minus gamma square plus 2 lambda gamma times I. Okay. Okay. This I is imaginary I. Okay. Then I can also now want to make some trick, so that I can actually extract the original initial phase of the displacement out of this amplitude, complex amplitude B. So, I can now write, let us set B is equal to some B e to the power I delta, where B is real. Okay. And this delta is also real. So, that delta will finally be the initial phase of the final particular integral in the displacement. Okay. So, if we do that, then of course, we have to write that. So, B, that is nothing but B cos delta plus I sin delta is equal to, I now take this expression f by m, this one f by m omega 0 square minus gamma square plus 2 I lambda gamma. So, this will be simply f by m, I just write this one a little bit separately here. So, omega 0 square minus gamma square plus 2 I lambda gamma. Okay. So, this is the whole thing over here, and now I have to actually express this whole thing as A plus IB type of thing, and then I will actually make this equality with this thing. Okay. So, I can try to do that as well. So, you know, the most common thing we do, we write this and we write like this. So, omega 0 square minus gamma square minus 2 I lambda gamma by, so this I just multiply the denominator and the numerator by the complex conjugate of this thing, so that the denominator becomes real. So, what will be this? This will be omega 0 square minus gamma square whole square, and then a plus b, a minus b, but there is an I, so it should be plus 4 lambda square gamma square. Okay. And if you write now like this, then specifically you can say that you have a form which is a plus b, a minus b. So, comparing, I just change a little bit again the color. So, comparing, we get b cos delta will be equal to f by m omega 0 square, minus gamma square by the whole thing omega 0 square minus gamma square whole square plus 4 lambda square gamma square. Okay. And I can write b sin delta will be equal to f by m. So, which will now be with a minus sign, of course, it will come, let me just check, yes, it will come with a minus sign, minus 2 lambda gamma by the whole thing omega 0 square minus gamma square plus 4 lambda square gamma square. Okay. So, b will simply be root over b square cos square delta plus b square sin square delta, and this will be given by again. So, if you do again the squaring and adding everything, so you will actually find that will give you. So, f by m will be common, and inside the bracket you will have. So, I can take like this, you can check this afterwards, I can do like this. Okay. So, it should be omega 0 square minus gamma square whole square plus 4 lambda square gamma square. Okay. And the numerator will be, the denominator will be the square of this. Okay. So, the denominator will be omega 0 square minus gamma square whole square plus 4 lambda square gamma square, but its whole square. Okay. So, now there is already one factor, one of this whole thing will go away, this thing. Okay. And finally, you will be given one of this and there will be a root. So, final expression for b, I write in red, will be equal to f by m root omega 0 square minus gamma square whole square plus 4 lambda square gamma square. Okay. And in the same way, you can also write an expression for delta. How to do? You just have to divide this thing by this thing. Okay. So, if you do now that, clearly you will find that you will have, so tan delta, I just again try to tell you there is a minus sign. So, do not forget that minus sign, you will find tan delta will be equal to b sin delta by b cos delta, which will be equal to 2 lambda gamma by gamma square minus omega 0 square. Okay. So, you now know what delta is and what b is. So, you can finally write that okay, my z is nothing but b to the power I gamma t. I write b as b e to the I delta times e to the I gamma t. So, this b times e to the I gamma t plus delta will be my z. So, then x t, the displacement will be equal to real of z, and that will simply be equal to b cos gamma t plus delta. And if you write this, then b you know and delta you also know, but delta you do not have to put now, but b you can put. So, it will simply be f by m root over omega 0 square minus gamma square whole square plus 4 lambda square gamma square times cos gamma t plus delta. Okay. So, you see this is what? This is the particular integral, but we do not have to forget that there is a complementary function as well. So, now how to find that complementary function? For complementary function we have to go through this equation once again, and now the complementary function comes from the solution of this equation and not the just the simple harmonic oscillators equation. That will, the complementary function will be now the solution for a damped unforced harmonic oscillator solution. So, which one to take? In general we know that there are 3 cases possible. So, if this is over damped or critically damped, then in any case that complementary function quickly decays, so finally it does not survive after some finite t. However, if you want to just keep alive a little bit of the reminiscence of this complementary function in the solution, the best way is to take the case of underdamped oscillation, okay, where your damping coefficient is less than the natural frequency, and that is exactly we will see here when I write finally the final. So, the final solution is x t. So, I actually can write this is x p because this is particular integral part. X t is equal to x c, which is the complementary function. I can call them like this x p t, okay, and I can write some a e to the power lambda t minus lambda t cos omega 0 t plus alpha. Okay. Alpha is some initial phase for the displacement, okay, without forcing, plus b is now f by m root over omega 0 square minus gamma square whole square plus 4 lambda square gamma square. Okay. Then I can say cos gamma t plus delta, and this actually finally completes my purpose or serves my purpose completely. Okay. That means, I now know what my displacement vector displacement is as a function of time, then I can do x dot, x double dot and everything. I can do actually x dot and find the kinematics. Okay. So, what is the, so this is a solution for a 1D harmonic oscillator with both forcing plus damping. Okay. For damping I just took deliberately this underdamped case, so that it can have some reminiscent after some t, otherwise it will decay very quickly. Okay. Now, coming to this part, you see there is a stark difference between this case and the case where there was no damping. Where there was no damping, we actually found that the amplitude blows up, okay, when omega 0 is equal to gamma. But here, even when omega 0 is equal to gamma, the amplitude is not blowing up, because you have a lambda, non-zero lambda, the dissipation. Okay. So, you again see if your medium has no dissipation, so lambda is 0, again you will have this problematic case where your amplitude is blowing up. Okay. Now, here what is happening, why it is not blowing up? Because if it blows up, you have to then go for a new type of solution which is linearly increasing, because here in this system the energy is fed by the forcing, but it is also dissipated by the dissipation term. So, there is a sink of energy, there is a source of energy. When there is no dissipation, just only forcing, it is only facing a source of energy. Okay. So, and when there is no forcing, only dissipation, it just faces a sink of energy. So, in case of a damping without forced, in case of a damped oscillator without forcing, you always have that after some time the displacement decays. That is only because the energy is only dissipated. There is no injection of energy. Okay. Here in this case, you will see that there is a competition between the energy injection and the energy dissipation. Okay. And now the point, and that is why we do not have any case of suddenly decaying the whole thing, because this part is the competitive part. This part is again the dissipative part, purely dissipative part. This part is the competitive part where you have both forcing and dissipations are in action, and your even for omega 0 is equal to gamma, you do not have a unphysical amplitude here, or you do not have an amplitude which is linearly increasing with t, you just have a constant amplitude over here. So, then the point is, should we call this thing as resonance, or should we rethink the concept of resonance? Then people say, okay, let us call resonance, instead of saying that okay, resonance is just a case where omega 0 is equal to gamma, or where the frequency of the periodic force is equal to the natural frequency of the oscillator. Instead of saying so, can we now think a little bit differently? Then people say, yes, let us do something much more physically understandable, and we call the case of resonance a case where the amplitude, okay, becomes the maximum. So, you see, then the point is that for which combination of this omega 0, gamma and lambda, you have this force, this amplitude part to be maximum. Okay. So, I just extract this expression over here. So, I can write this expression B is equal to f by m root over omega 0 square minus gamma square plus 4 lambda square gamma square. Okay. That to be maximum at resonance. So, we have somehow reconstructed the concept of resonance here. Okay. So, resonance actually is a sense, you see, that where there is a very good understanding between the oscillator and its ambience. So, that it has the maximum gain in terms of amplitude. Okay. So, when you have a resonance, then this should be maximum, and for that of course, you know that somehow if this is fixed, the amplitude of the f, and if this is fixed, this is the mass of the oscillator, then of course, we have to play with this factor, and we know for given f and m, which we cannot change, okay, B is maximum if root over omega 0 square minus gamma square whole square plus 4 lambda square gamma square is minimum. Now, there is a very common trap where the students may be trapped. Okay. The trap is that at this point you can think, okay, so what is the minimum value? So, this is actually the sum of two perfect squares, and this one can actually be 0 when, so this can have a minimum value when this one is 0, and that means again for omega 0 is equal to gamma, you have the minimum value of this thing, of this whole expression to be possible. This is not right. We have to first think that which quantity we can change or which quantity we can tune. Okay. So, here you see once again, when an oscillator is made, then its omega 0 is already given. A medium is also given. So, that means lambda and omega 0 we cannot touch. So, omega 0 is determined by the nature of the oscillator. Lambda is determined. So, lambda actually you can change, but here I am just thinking that lambda is just, I mean we do not touch lambda, is determined by the medium, and here we do not touch it. Okay. So, the only tuning parameter is gamma. So, that is why I have to actually do something else, I have to actually find gamma. So, to find gamma, for which this root over omega 0 square minus gamma square whole square plus 4 lambda square gamma square is minimum. Now, once again, since both of them are positive definite, then I can also say finding minimum of this thing and or the square of this thing, they are the same. So, or for which omega 0 square minus gamma square whole square plus 4 lambda square gamma square is minimum. Okay. And what to do for that? We have to do dd gamma omega 0 square minus gamma square whole square plus 4 lambda square gamma square to be equal to 0. We can also check with the second order derivative, that you can do yourself, okay? And I can guarantee that you will find that this will give you a minimum. Okay? So, if this is true, then 2 omega 0 square minus gamma square times minus gamma square. So, it will be minus 2 gamma plus 4 lambda square times 2 gamma is equal to 0. So, then I can actually write, so this will go away, yes. So, finally, I will write that omega 0 square minus gamma square is, yes, with a minus sign. So, that can go to the other side, is equal to 2 lambda square, or you can say that my gamma square will be equal to omega 0 square minus 2 lambda square, or you can say simply this will be equal to root over this. Now, you see, according to our new understanding of resonance, this will be the resonance condition. Okay. Now, it also depends on people. Some people can be a little bit, like non-flexible, rigid. They can say, well, I choose to call resonance when omega 0 is equal to gamma. Okay. But you say that, okay, if we just try to be much more realistic, and even if you do somehow in the afterwards, like the current electricity or electronics, you will see that this is the definition of resonance, which is much more practical, and this will actually give you that the gamma, which is the force frequency, periodic force frequency, should be such that it should be equal to root over omega 0 square minus 2 lambda square. Now, if you have a medium where there is no dissipation, then lambda is 0, and the resonance condition simply boils down to gamma is equal to omega 0. You see, in physics, that is always a good thing, that you can always check the consistency of your model or of your formula by using appropriate limits. That is exactly the case over here. Okay. Thank you.